So I sent out revised lecture notes, kind of unusual, before the lecture. The reason is I've recently made a lot of progress with Helmholtz resonances, and it's a thesis topic, and I just couldn't let I just had to revise it. So I directly emailed it all to all of you, and including the distance learning students, of course, and Gene will post it soon, update the Sakai. Okay, so this is in chapter 10. We're nowhere near chapter 10 yet, but it comes up an experiment. So I'm going to ask you to accept a few things here that will, some of them will eventually prove, but it's not too bad. Okay, so we begin here with a volume. Normally it's a rigid volume with a neck connected to it like this. So this is a cavity with a neck. An example, there's plenty of examples of this: wine bottles, beer bottles, all kinds of drink bottles, plastic bottles, Christmas ornaments if you remove the stems. All right, and a really annoying one if you have children. And you guys know this? Are you guys aware of this? Okay, yeah, really annoying. I remember driving our parents crazy with doing this. And these systems have it's interesting, has a lot of occurrences and applications, as I'll explain to you. It has a low frequency resonance. It's called a Helmholtz resonance. And when they're a resonator exhibiting a Helmholtz resonance is called a Helmholtz resonator. And here's let me give you an example here, a demo. Here's a flask. You see a glass flask, and if I blow on it in an appropriate way, you can hear a very nice tone, right? It's measured to be 174 hertz. So that's we'll calculate the wavelength. I think it's about 2 meters. It's much larger than the size of the system. Okay. Now, the most accurate way to measure this is to put a little microphone in there on some thin wires, dangle it in there, and you get a really nice signal. It's a great, oscillator. It's a really nice resonance, and you will do that in the experiment. You'll accurately determine the resonant frequency, and you'll compare to the theoretical. We'll talk about the theory now. So this is actually I already need to edit this. This is occurrences and applications. Okay, they were used by Helmholtz in 1800s to determine the frequency of a pure tone. So if you've got some pure tone and you bring up a Helmholtz resonator and you listen carefully, and you're not going to believe this, but the way they did it, how do I know if this thing's resonating or not? In the presence of a sound wave, it's not so obvious. Okay, in the experiment, like I said, you will do it by putting the microphone inside, which you're picking up on mainly just that resonance. You'll very clearly see it. So how do you think they did it? Well, they made these with a little open nipple right here, and they stuck them in their ear like that. But I'm not kidding. Okay, we used to have a set of these, actually, and it's disappeared over time. But I always wondered what they were. And somebody told me eventually. So Helmholtz was the first one to do that. That's why they're called Helmholtz resonators. They have a lot of current usage, as I'll explain to you right now. They're commonly used in ducts. If you've got sound, unwanted sound, some kind of air conditioning or heating duct, and it's roughly a pure tone, you can tack on a Helmholtz resonator in the duct there and tune it to be approximately that frequency. And because of the resonance, it'll resonate. That energy has to come from somewhere. It comes from the sound wave. So you can dampen sound in ducts. It's very common. they've used them at the National Institute of Standards to accurately determine thermodynamic quantities of the fluid. For example, the speed of sound. And I'll describe their arrangement a little later in the lecture. But the resonance here, the formula that we're going to develop, depends upon the speed of sound. So if you can accurately measure everything, including the resonant frequency, you can back out, you can get the speed of sound. So this is a resonance, and it can be used to amplify a source. And the most common example that you've all heard is this. So here's a loudspeaker, the same one I brought out, I think, a few days ago. That's 100 hertz. It doesn't matter as long as it's roughly low frequency. That's 100 hertz. And do you see this port right here? Okay. There's a Helmholtz resonant. And it's tuned such that and made such that it's a broad resonance. And it's done to amplify the low frequencies. And it's very easy to hear the difference. I'm going to close it and open it, okay? Now I can clearly hear it, but I don't know what you guys hear. Yeah, it's very, very clear to hear. So, now just a quick note, very quick. One of the professors who used to teach the transducers course, the 4454, he said that historically, somebody stumbled, a non-scientist, non-engineer stumbled onto this in like the 70s, roughly in the 1970s, and tried to popularize it and get more scientists, engineers interested in it, and nobody paid any attention to him. Okay, finally they recognized that, oh yeah, there's something there. It really is working. Okay, and then they did the theory, and the theory is very complicated. That's what this professor, and he's a transducer expert. And he actually teaches some of the theory when he taught the transducers course. But he said it's actually very common, very complicated theory to prove it. But you can clearly hear that it works, right? It's called bass reflex. Here's something I stumbled onto about a year ago when I was doing a literature search for an article we published early this calendar year. There was this flurry of research in the 2000s on what they call synthetic jets. And what these are is a Helmholtz resonator, a small Helmholtz resonator, and you'll see why, you'll understand why in a minute, where they put some kind of driver inside here, a piezoelectric type driver that vibrates. You put an oscillating voltage across there and it'll expand and contract. And the purpose of this is if the amplitude's sufficiently high here, what happens is you get a jet coming out here. This is very easy to demonstrate. I'm not going to demonstrate it for you, but you routinely do it in the nonlinear course. You can put out a match, a lit match, a flame can be extinguished. And there was all of this attention. I kept running into all these papers. So finally I said, well, I better read some of these, a little bit of these papers, Imagine that, reading a paper. So what they were interested in was manufacturing banks of these, ultimately making them very small, putting them on an object like a wing, an aircraft, in order to control the flow. For example, when air goes over a wing, it will typically separate there. If you can reduce, it's called separation of the boundary layer, if you can reduce that, you can reduce significantly the drag on the aircraft. So I don't know what the current status of this is, but there was this flurry of research. And it involves Helmholtz resonators. Helmholtz resonators just refuse to die, okay? They just come up a lot. Professor Kopolka recently told me they've been proposed to use for energy harvesting. This is, believe it or not, I heard this on NPR about 2 years ago, National Public Radio, about 2 years ago. People are trying to harvest energy everywhere, and they're trying to harvest acoustic energy. Even though there's just not much energy in sound, they're working on it. So the Helmholtz resonators have apparently been proposed there. She also told me, Professor Kopolka also told me that she was talking to submariner once, and there was this huge noise on a submarine that was generated. There was some Helmholtz resonator on the hull of the submarine. So they can be unwanted resonances. How many of you have been driving down on a road with one window open and you hear this very low frequency? That's almost certainly a Helmholtz resonance. We haven't calculated, we haven't explored it quantitatively yet, but it's very long wavelength. I think it has to be a Helmholtz resonance. And the long wavelength nature we're going to talk about right now. Unfortunately, it's hard to reproduce that automobile effect, right? So it's kind of hard to do experiments there. Okay, so what's going on here? Well, the first thing you want to notice is, and I've already mentioned it twice, is that the wavelength is very large here. If you take the speed of sound in air, divide it by the measured frequency of the Helmholtz resonator there, you get 2 meters. And you know what 2 meters is. It's big. It's much bigger than the size of this resonator. So it's not a pipe mode. A pipe mode, what we call, is like a wave on a string, a standing wave on a string that you did last quarter, and then the standing waves that you did this quarter, the standing sound waves, where you have a wavelength that's, you know, comparable to the size of the, comparable to or less than the size of the resonator, right? Something else is going on here. What's going on? Well, here's sort of the standard explanation. Is this. There's a, you can think of the fluid in the neck here is acting like a plug of mass. And what it's doing is, in the Helmholtz resonance, it's oscillating back and forth, radiating sound that we hear normally, right? And why does it oscillate? Well, it's got, what do you need for an oscillation, for an oscillator? You need inertia and you need stiffness, right? So the inertia is just the mass of the plug. Do you see the stiffness? Do you see the spring here? When it's moving this way, the gas compresses in here. When it moves in that way, it expands. So that's the spring. It's the Helmholtz resonance, to a rough approximation, and we'll refine that in a little while, is a mass on a spring. And that allows us to calculate the frequency, and we'll do that. But I think there's something else before that. Oh, now this is, I've lumped this system here. I've lumped the system, all the inertia is in here and all the stiffness is here. As long as this cavity is small compared to this, we won't have to worry about the inertia in here, because this plug going in here, this motion gets distributed over the whole thing. There's approximately uniform compression and expansion here. And because the frequency is low, you're not going to get any wavelengths in here, okay? The wavelength is huge here. So when this is moving, you get approximately uniform compressions and expansions here. Now here's an interesting question that'll actually come up a little later, I think, is we have this Helmholtz resonance with this very long wavelengths, right? What if you, and so imagine that you have that's oscillating. There's no dissipation, just imagine in your head, this is a Gedanken experiment, right? Imagine that this mode is excited here and there's no damping. So ignore the radiation, okay? Or typically the radiation damping is very small anyway, as you will discover in the analysis of the experiment. But imagine that you have this mode that's excited here, and then you slowly distort the resonator into this. This is what we call a quarter wavelength pipe, because the fundamental mode here, the lowest frequency mode, the pressure will be an antinode there. It'll be a node here. You get pressure release. So it'll be a quarter of a wavelength. You plot the pressure, acoustic pressure, it'll be 0 here, and it'll be oscillating. It'll be an antinode there. So as you imagine this being distorted, what's going to happen to the frequency? We start off with the frequency here corresponding to a wavelength like that. We get down to where this is a quarter of a wavelength. So the wavelength has gone down. The frequency will go up. Okay? This is a useful, a lot of times it comes up in acoustics, particularly experimental acoustics, this idea of mapping modes. The Helmholtz mode will map into the quarter wavelength mode here. It'll continuously go from this mass on a spring to this continuous, non-lumped system, standing wave. Okay, so how do we do the theory? We've already set it up here in this diagram. If we know the inertia here. It's this mass. We can calculate that. It's just the cross-sectional area, S, times the length, times the density. What about the stiffness? If we know the stiffness, then you know what the frequency is going to be. It's just going to be the square root of the stiffness divided by the mass. So we need to get the stiffness due to uniform compressions and expansions of the air in a cavity like that, or like this. So if I'm going to call this X positive this way. So if the plug is displaced over here some distance, okay, there's going to be a compression of the gas in here. And we need to calculate that. And it can be done in one line. It's a long line. Here it is. We need to know how the pressure, to get the stiffness, we want to know how the pressure is changing with X. Okay, that's going to give us the stiffness, lead us to the stiffness. How is the pressure going up? Well, the pressure, again, I use this all the time. The C squared is how the pressure changes with density. So we can write this. What's the change in density in there? When X is positive, the density goes up. The density is the total mass in the cavity divided by the total volume. The volume is changing. The mass is staying the same. That's our perspective here. So when I take the differential here, mass is constant, the volume is changing. I get this. I'm just taking a differential. And now the change in volume is the cross-sectional area times X, right? That's going to be the change in volume. So we multiply by the cross-sectional area here to get the force, the restoring force due to the compressing and expanding gas in the cavity. And we get the force it's a restoring force, there's a minus sign there, and it's proportional to the displacement for small displacements. And what's that? That's the spring constant. That's what we need. So we identify the spring constant here, and now we can calculate the frequency. That's all there is to it. But we've made approximations here, and we'll talk about those in a minute. So here it is, square root of kappa, the spring constant divided by the mass. We substitute our expressions and simplify, and we get this. That's the predicted, from our theory, that's the predicted frequency for a Helmholtz resonator, for the resonance. And it's not boxed, and it's not boxed for a reason. The reason is, it almost always does not agree with experiment. It's typically not a huge deviation, but it's noticeable. It's noticeable. And in fact, in a later demonstration, if I remember, I think I will. I'll point out to you. You'll hear the difference. You'll actually literally hear the difference. So there's a problem here. It turns out when you take measurements, the actual frequency is less than this value. All right? So what's going on here? So here's the latest way that I'm explaining this. That I think, well, let me just run this by you. Is this really what's going on here, this picture? This usually bothers students anyway. This kind of looks artificial, right? Is this plug really going to go and stay intact like that? No. What's really going to happen is, when the fluid is moving in here, once the fluid gets in here, it's going to diverge pretty rapidly. It's going to rapidly diverge. All right? So you say, oh, we're losing that mass. Yeah, but what's happening at the other end? There's a convergence here. So the mass this little bit here that we've lost that's gone into there will appear over here. So we have this kind of strange situation where we have this plug of mass The mass is constant. It's equal to the equilibrium, the mass in here, the density times the cross-section area times the length. It's constant. And there's motion, but the plug itself is actually not moving because when there's particle motion this way, this diverges, this comes in here, the plug is kind of sitting there. Now, you can use that idea to calculate, to go through the calculation. Because the plug of the mass is the same here in our calculation as it is in the more correct, the more proper one, it turns out they're equivalent calculations. I've done this. So this calculation has led us pretty quickly to an answer. This is the typical one in books, incidentally. And then they just make a little brief comment about what's going on in the ends. But you can also calculate this by assuming that this mass just immediately spreads out, slows up immediately and spreads out in here. So now the volume is constant, but the mass is changing. We had constant mass in the cavity, but the volume was changing, okay? So you're starting to see how they look like they could be equivalent. They are. They're equivalent calculations. But this is a better physical, this is more appropriate here. We get this, what's going on. And it points out something very important. Even though we expect for a large cavity here, there's going to be quick divergence here. There's still going to be some motion there, right? There's going to be mass here, right near the opening, and mass over here at the same time that's participating in the motion. We have not included that mass in our inertia. So what effect do you think that this diverging and converging is going to have on the frequency? What's it going to do to the frequency? It's going to make it go down. Exactly. There's inertia that we haven't accounted for. How do you calculate that? Well, that's difficult, okay? And it was finally done for the first time by Rayleigh in the late 1800s, and we're going to go through that. We're going to see that calculation. Our approach is going to be different. But I'll have more to say about how that's calculated in a minute. But let me give you the results here. Here are the results of calculations that have been confirmed. And they've been confirmed. The way we think of it, which is really convenient, is, and so convenient that you can deal with it and not know anything about what's going on here. Because there's added inertia, effectively this neck length is longer. It has a geometrical length. Its acoustic length is typically a little longer. People have calculated that little bit of distance, typically a little bit of distance. It's called an end correction. And it's been calculated in a number of cases. Here are the two extreme cases that we will deal with here. In the cavity, okay, what you see here, for the end correction here, this is approximately, roughly, a baffle, a planar baffle. All right? So there's an end correction here. You have to add on and a little bit of extra mass there, right? Here, the end correction is different because there's no baffle. And the flow here is more confined because of this surface right here. It spreads out more here. So there's greater kinetic energy. There's greater mass here. So that end correction, this end correction is bigger than this end correction. And here's what the end corrections are. They scale with the radius. Assuming a circle here, people have calculated them for circular. They scale with the radius, and here they are. So when you're dealing with a baffled end, or a flange, also known as a flanged end, here is the correction. Originally calculated by Rayleigh, you can see this is an analytical result. It's approximate. And to two figures, it's 0.85 times the radius. What about the free end with no baffle? Well, that took World War II for that problem to be solved, and I'll describe that to you briefly in a minute. But the result is this. It's less, the end correction is less, as I just described to you, because the flow spreads out more here. It's more confined here, so you get greater kinetic energy. There's greater inertia here. And it's equal to 0.61 times A. So you're going to use this in the experiment. So before we go we can now patch up the theory by using this effective length. All right, but before we do that, I want to mention some interesting historical notes here. So Rayleigh found he could analytically do it, and we'll go through essentially this calculation. In the limit of long wavelengths, so that means long wavelength compared to the radius here of the neck. He did this in roughly the late 1800s. KFCS gives the effective length due to the unflanged to only one figure. Now that may not seem like important to you, but I see it as there's an indication. This is complicated, okay? And again, this problem was not solved until World War II. It was solved because of radar, and I'll talk about that in a minute. But anyway, KFCS have 0.6A. If you dig into the literature, all right, you'll find that it is known to the next figure. It's only known through intensive numerical analysis, incidentally, computer simulations, essentially. It's 0.61. You want to use 0.61, and I think we wrote that into the laboratory handout, okay? Gives you another figure there. So the problem that was around during World War II and became very important because of radar was, what is the radiation field from an unflanged pipe? So Rayleigh had solved the problem, the acoustic problem, which is similar to the electromagnetic problem. That if you have a pipe here and you have this very large flange and you have a wave, let me just write it like this. You've got a wave coming down here. It's going to radiate out like this. You're going to have a radiation pattern. Rayleigh's solved. You can solve for that radiation pattern. But what they wanted for radar, they wanted this problem, okay? And no one had been able to solve it. And it's a famous problem, and it goes under the, and went, and still does, go under the name of radiation from an unflanged pipe. And two people did it during the war. One of them was Schwinger in the United States and Weinstein in Russia. They independently did it. Weinstein developed a new mathematical method to solve the problem, and he eventually wrote a book on that. Schwinger went on. Schwinger's a physicist. I don't know what Weinstein was. Schwinger went on to get involved in quantum electrodynamics. You guys know what that is? That's a relativistic quantum theory of electrons and photons. It was where virtual particles were discovered. You guys know about this? You'll probably hear about some of that in the colloquium, which is a week from tomorrow, right? Okay. Anyway, Schwinger eventually won the Nobel Prize for this work. He shared it with Feynman and Tominaga, Japanese physicists. And it's amazing to my generation, but there are students out there who don't know who Feynman was. Do you guys know who Feynman was? Famous physicist, very energetic guy at Caltech. I heard him speak a number of times because I was a graduate student at UCLA. He's most famous. He was the one who was on the committee that was investigating the Space Shuttle Challenger disaster back in the 80s. He was the one who did the demonstration with the O-ring, dunked it into ice water, and showed that it became brittle, and that was the cause of the accident. Do you guys know about that? Okay, good. Yeah, I hope, it's not good to forget. We want to remember things like this. Anyway, Feynman, that was just one of the many things that he did. So I actually have, not by choice, but I have a history of involvement with incorrections. Okay? They just keep coming up. I worked part-time in industry for a while, for Northrop Aircraft. And I've mentioned this to you guys before, but when you have an engine, a jet engine duct, like this, with compressor blades at the end here, and it's being hit with radar, the radar, some of it gets absorbed, comes in here, bounces off the end, and then re-radiates in all directions. And you can track that. So, the dealing with this involves the radiation that comes out here is the radiation from an unflanged pipe. So I had to understand this and work on the computer code to calculate this. to understand it, I had the choice. I could look at Schwinger's article, journal article, very compact, very difficult to understand, right? Or I can go to this book that Weinstein wrote where he explains everything. So we used Weinstein's book. That's where I first encountered this. It was great that he had written that book. And interestingly enough, I was later actually a TA for Schwinger in his quantum electrodynamics course. It was a tough course, academic year. That's about all I did that year was take notes that he edited. I didn't get a lot of other work done that whole academic year. And then, years later, I was working with a student, some students worked on this, and a colleague, actually a postdoc. We had to deal with the thick end correction. You know, there's this case, that's an extreme case, and then there's the extreme case where it's thin. What about in between? That can come up, okay? Well, it wasn't until I think it was the late 60s that was solved by a famous Japanese acoustician named Ando. So we had to use this in our research, the thick end correction, in between. I think we got results off graphs in the journal article. I think that's how we did it. And the reason we had to do that is the research involved these certain types of resonators that we call variably non-uniform. And let me demonstrate them for you. Here's one. Okay, this is acrylic. See, it's been bored out, and you can clearly see, I think, that there's a different diameter here than here, right? If I slap the end, you hear a tone. I'm exciting the fundamental, almost predominantly the fundamental acoustic mode in here. Okay? What if I reverse it? So instead of doing this, I'm going to do this. Huge difference. And in fact, anybody musical in here? God, I'm sorry, I'm not sealing it well. I didn't practice enough. It's almost an octave, twice the frequency. Remember we talked about octaves, musical octaves? So this was carefully machined, and we used the theory that we developed for this without the end correction. And you can hear it needs to go up to be an octave. So we recognized that we needed to include the end correction. So that's why I went to Ando's work, and then we redesigned a whole set of these, many more of these. These are the original ones. I'm not showing you those. They're all boxed up. I can get them out, but it's easier to use these. Okay, and then we throw these around. We don't throw the other ones around. Well, you can imagine here, if you imagine cutting this, okay, into two halves. The ratio of the diameters is different here, but you can see there's a step there, right? Can you see that? Can you see the step there? Does it show up? No. So you can see the step there. Why would you want to do this? Well, the reason is now you can get a third frequency. You can get this one, you can get that one, and then you can get one where it just makes a jog. So if you go through the calculation, you can come up with a musical scale, the first three notes of a major scale. Okay. Now again, that's not quite right. We don't have the end correction here, but we used the end correction, and we got close to musical intervals. Now. You don't want to hold your breath. I don't think this will ever appear in any kind of musical performance. It's not really useful, okay, musically. But it is interesting, and it brings up the importance of the end correction. Okay, so here's what we've got. Here, if you look back at that formula that we got, the plug formula, assuming that the divergence and convergence is very quick and we ignore those end effects going on there. We got this formula where L is the geometric length. So all we do now, they've made this easy on us. All you got to do is replace the geometric length with this effectively greater length. And here it is. It's the geometric length plus the end correction. Now, for a Helmholtz resonator, it's approximately flanged on this end and open or free on this end, unflanged on the other end. So we add those two corrections. We add the Rayleigh and the Schwinger-Weinstein here. Hold on. The Rayleigh plus the other one, the unflanged end, and we get this. So this is what you will use in the experiment. 1.46 times the radius. That'll be, you'll test that. You will experimentally test that. I realized that I didn't explain to you. It's not in the notes. I didn't. Why is this frequency greater than that frequency? What does this look like to you, approximately? Starts with H, 2 words. First word is Helmholtz. Second word is resonator. It looks like a Helmholtz resonator, right? And you know that the wavelength is going to be big for Helmholtz resonance, right? Now, it's not, it doesn't really meet the requirements of having a small neck compared to the cavity, but still, it's roughly a Helmholtz resonator. What does this look like? So that's going to have a relatively low frequency. What does this look like? Well, if I imagine this to be even bigger, I've got a quarter wavelength here, which means it's going to have a wavelength like that. So here, it's going to have a huge wavelength. Here's smaller. That's one of the ways you can explain why the pitch is different here. It's one of the ways you can explain it. Okay, so here's something important. The distance learning students, I guess, don't have to worry about this. But 1 year that we did this, we had a bad experience. The students in the lab, the Helmholtz frequency is the Helmholtz resonance will give you the lowest frequency, lowest acoustic frequency you can have in here, right? But if you're sweeping for it, you could miss it and go to a higher frequency, one of the pipe type modes, much higher frequency. So some of the groups, a lot of the groups, locked into this higher. They didn't measure the Helmholtz frequency. They were measuring a pipe mode frequency, similar to the first experiment, but distorted, because this is not a straight pipe, but similar to that, a higher frequency mode. So it's a very good idea for you to roughly calculate the frequencies you expect, and then go to that region and hunt for the Helmholtz resonance. Okay, and that only needs to be a rough calculation. You don't have to use the effective length, just use the geometric length. Just know the ballpark you're going to look for. And this happens a lot in acoustics, in experimental acoustics, where it's nice to know the region you want to look at, because there can be a lot going on in acoustics. So if you can narrow down the region, the search region, then it can help you a lot. Now, one thing interesting here is what happens, can we have L is equal to 0? Well, the math, I can certainly do the calculation. Will this theory still hold? Well, that's an interesting question, and I don't know if that's fully known yet. Okay, but that shouldn't stop us from doing a demonstration. So this is a plastic hollow, maybe it's a float or something. I walked by it for years. It was down in the anechoic control room of the anechoic chamber, or in Jay's lab. And then about 4 or 5 years ago, I walked by and I said, yeah, okay, we're going to drill a hole in this. So I took it down to the machinist. He drilled this nice 1-inch diameter hole, and he gave it to me, and then it's a Helmholtz resonator, right? The geometrical length of the neck is very small. It's very thin. But you can get a Helmholtz resonance without any neck at all. In fact, only a few days ago, I've been reading about this. Helmholtz he didn't have any necks in his resonators. His resonators just had holes. They were like this. I was amazed. Now there's an issue here. Just because you can zero this out in the formula, there could be some assumption in the theory that prevents you from doing that. This may only be valid if the incorrection is small compared to the length. And I actually suspect that there is some truth to that to some extent, but this is research. I don't know the answer yet. The first thing to do, of course, is measure this frequency and calculate it and compare the two. And we're about to do that. We haven't done it yet. Okay, so now we have our theory, right, with the incorrections. Let's take the demonstration. I've measured the distances here. Now, not real clear, right? Is it a spherical cavity? Well, kind of. It's got this flat part here, you know, so that you don't need something like this, so you can rest it. So, and look at the curvature here. Now, you guys have much greater, the resonators that we use for this have been made with aluminum inserts so that they're much more accurate than this for the experiment. The experiment's much more accurate. But that shouldn't stop us from just doing a rough calculation. So I took these rough measurements here, roughly to the nearest millimeter. Here, I think I chose the average diameter to, I don't know what I did here. It's in the calculation, okay? This is just going to be pretty rough. We don't expect really good precision here. But when you take the dimensions, plug them into the formula, with the incorrections, there's the combination of both ends. It's that 1.46, right, times A. And I wrote all this out so you could see. It's not very small. You know, what's 16 divided by 6? I guess it's 8 divided by 30. So it's 20-some%? No.
Like almost like almost a quarter.
Yeah. Right. Well, I'm not being too timid on this. I need to edit this. I didn't realize that. Let me make a note here. Yeah, it's not small, okay? Not small. That is typically the case. It's not very small. I think it's all I wrote here was not very small. So anyway, we plugged the numbers in. We need to find the volume. I took the average. Yeah, I can see I took the average diameter and plug it in with the effective length there. And we get 182 hertz. The measured value is 174 hertz. So that's a 5% deviation. The predicted is 5% higher. Incidentally, if you don't use the incorrection, you get 205 hertz, which is, I didn't calculate. You get 205 hertz, which is 12% or something. Not good, okay, without the incorrection. So that's what we hit in this thing to try to make we wanted to make those demonstrations dramatic. We wanted to make it musical intervals there. Incidentally, we published 2 papers on that, 2 scholarly articles on these resonators. A theory and an experimental paper. And if anyone's interested, I'd be very happy to email you the PDFs, okay, the journal PDFs. So anyway, we got this 5% error here, and that seems reasonable for the precision of these measurements. I haven't pursued this, but I want to point something out. I saw a JAZA article some years ago, a Journal of the Acoustical Society of America, where they concluded that the volume that you should use here, that it's better to use the total volume including the neck. Now the theory assumes a small neck compared to the cavity, so it's a small difference, but these people concluded that, and I've got to find that article and understand it. But if you do that here, if you include the neck volume, you do the total volume, then you get 1% error. Now that could be, that's not necessarily, it could be that it does support this, but it could be just a coincidence. These aren't really these aren't precision measurements because it's not a precision, you know, it's got all those curves and flat bottom and all that. So it could be just a coincidence that it got better. But it is intriguing, isn't it? I think in the experiment this time we should look at this. We should see what happens. We've never done this before. We need to get some, I don't know if everyone has to do it, but some of the more enterprising, some of the students who find this experiment more interesting than others, or other students and other experiments, maybe have you see what happens if you do the total volume. See if that helps things. You might want to do that. I think that would be good. And then I'll try to find that article somehow. All right, so here's some examples. This is a double cavity Helmholtz resonator. And this is what I distinctly remember hearing a talk on this at an Acoustical Society meeting. I can't remember his name. Some guy from NIST was in a group, and they were exciting, probably with a little tiny piezoelectric driver in here, the Helmholtz mode here, and measure the frequency. And they were getting out the speed of sound. From the speed of sound, you can get the ratio of specific heats, right? Or if you know the ratio, if you're very confident in that, you can get the density. You can get thermodynamic information, basically. So they were doing that. They had very precision ones. They were, remember this. What's the frequency? What formula do you use for this? Well, you don't have to go back and redo the plug theory. We've got a mass here. We've got a spring here. What's over here? Another spring. So this system is equivalent to a situation that you've all seen. The resonant frequency here is there's an inertia, the mass here. And these are different. I've drawn them in general being different. The effective stiffness here is just the sum of the two. They add together. Okay? And if you go back and look at the theory, you'll see that and it's very physically reasonable, the stiffness here is inversely proportional to the volume. The bigger the volume, the easier it is to compress the volume. Pretty obvious. And it's an inverse proportion. You can go back and look at the theory. So the stiffnesses add, and they're inversely proportional to the volume. So all we do is we take our formula here with the effective length. I'll talk about that soon. But this volume here is going to be, you want to think of this as 1 over the volume. And the stiffness is proportional to 1 over the volume. So the stiffnesses add. So this V here, we replace 1 over V with 1 over V1 plus 1 over V2. And that's going to give you the theoretical value. One more thing we need, as I mentioned, is the effective length. They're both flanged. Both ends are flanged. So now it's 1.70. Here's something I only recognized last week. Because the last time I heard this annoying Helmholtz resonance, which we're almost certain is a Helmholtz resonance, in a car, was a long time ago, decades ago. And I remember thinking, oh, that's an acoustic resonance. I don't think I knew about Helmholtz resonance. I think this was a really long time ago. But I immediately opened up the other window, and it went away. Okay, so I had like the driver window open. I had this annoying, it's really annoying, right? Everyone seems to agree. Okay. I just cracked the other window, and it went away. And then I think years later I said, oh, I killed the Helmholtz resonance. No. Then last week I realized, no, there's a Helmholtz resonance here. So here's a model. It's kind of simple. I'm going to the symmetric case here. Okay? This has a Helmholtz resonance. Does this have a Helmholtz resonance? Yeah. And what it looks like is this. You got a plug here, plug here. They're moving in antiphase like this. You get compressions and expansions. So what does it look like? Something you've all seen before, right? It's this. It's that. So you can calculate it. And the easy way to see it here is you can compare this case to this case. So here it's closed off, right? This is going to have a certain frequency. How does this case differ from that? Well, imagine a boundary right here. I see a Helmholtz resonator here. I see the same Helmholtz resonator here. They're going at the same frequency. The frequency of this will be the same as the frequency if I cut this in half. So I've halved the volume. I've doubled the stiffness. So the frequency will go up by the square root of 2. Because remember, there's a square root. Oh, I've erased it. Omega is the square root of the stiffness divided by. Okay, I think there's one more thing here. Yeah. This is the only experiment in the acoustic sequence, as far as I know, where you will compare a measured quality factor to a theoretical quality factor. It's often hard to calculate theoretical quality factors. You can do it for a mass on a spring, okay, if you know the damping parameter. You did that in 3119, but we're talking about acoustics here, right? So, so how do you get the quality factor? Well, there you're just going to look it up, okay? We are going to deal with damping in this course, but we don't have time to go through the case of here, for example, this plug going back and forth. There's viscosity. There's scrubbing due to viscosity at the neck here. That's a loss of energy. And that's going to lower your quality factor, okay? There's, of course, radiation. The radiation represents energy that's lost. So that's going to contribute to the quality factor. And then finally, due to the compressions and expansions in here, when there's a compression here, it's a little hotter, there can be some heat flow. You're losing energy. Okay, so there are 3 sources of dissipation for the quality factor for a Helmholtz. NIST, why do you think NIST closed this off here? The main reason. They don't have to worry about radiation. Yeah, right. And there's other reasons why you might want to do that. But we have these 3 sources. So you're going to do what everybody else in the world does. You're going to open up KFCS and find you're given some of the quality factor information in the handout. But one of them, I think, whoever wrote that a long time ago, they're forcing you to go into KFCS, I think. Unless I added it, I can't remember. But this is the main use of KFCS. It's a reference book, okay? I told you guys this, I think, at the beginning of the quarter. People go in there, they want information, they want it now, and and they want it right, and they want it to be right. So you guys get to have that experience here. Unfortunately, we're not going to be able to calculate. We're going to do calculations on the radiation, but we're going to talk about dissipation of sound, but we can't get into the pipe dissipation. We just don't have time. Or this dissipation. This is essentially a pipe effect, a surface effect, a boundary effect. So you're just going to use the results and compare to the measured values. Any quick questions? Okay.